Argument and Lurk in 2025. Where are we so far? What are we doing with this company that has very nice Hornet-themed t-shirts? We're looking at what proving is actually looking like today, right? And proving today is a bit of an ISA fest. So this day, company after company after company since 2023 has latched on the idea that, hey, you know what, there's those instruction set architectures that are everywhere, and I have project after project after project that has figured out that VMs are really cool. ZK VMs are really cool, and especially the ones that have a generic instruction set architecture. They can take something that looks remotely like a CPU, and the idea is you're going to take your code, compile it to that instruction set architecture, and then you're going to have a proof, and it's great, and it's done, right? And to interpret this, you have to compare it to what you have before this. That is, before this, you had two models, right? You had the ISA model, and then the compilation to a circuit model. So the compilation to a circuit model, we all know, it's the circum model, right? The circum model is you write circum code and it compiles to a circum circuit. Nice thing, you get performance. Not so nice thing, it's a kind of a bitch to write a correct circum program, to excuse my French. Then VM is a lot more intuitive. It gets you back the intuition you have as a programmer. If you are running a loop, you don't care that it is provable that you will run 50 times through this loop and not 51 times. If your loop is early stopping, you only pay for the iterations that you actually ran. If you are doing branching, if you are an if, you're not paying for the complexity of both branches of your if, but only the if branch that you use, right? That's why we all like VMs. But there's one subtlety, which is this TCB acronym that is in my slide here, which is Trusted Computing Base. The Trusted Computing Base is basically what is the amount of code that needs to be correct for my prover to be correct, for my proof protocol to be correct. So Bob and Charlie are playing a game of ZK Battleship. What do I need as safe code to make sure that this game of ZK Battleship runs correctly? And the compiler is in there, right? That is, your ZK VM must be bug-free in order for the proof to hold and really prove what you intended to prove. But the compiler must also be bug-free for the protocol to prove that the ZK Battleship program you agreed to in Rust, in that high-level language, matches the thing that you're actually proving, which is the RISC-V ASA. So if you retain absolutely nothing else from this talk, you might want to retain that. We have a lot of data on compiler bugs. Compilers such as GCC and LLVM have been studied for decades. We have decades of back data on their bugs. And we have very nice researchers that have been pointing out and sorting by hand which bugs are optimization bugs and which bugs are, I don't know, the UX or the command line interface option number 42 being incorrect. And sorting that manually, they have gotten results. You have all the details in our blog post of us. There are several publications that all agree on that topic, which is that on average, on each of GCC or LLVM, you get 6 new misoptimization bugs. And those misoptimization bugs are chosen very specifically because they look like something that the compiler is doing post-compilation, where the compiler is, in that bug, violating the semantics of the code you've given it. So you give it a function to compute, and you're saying, here's the source code to a function that computes f of x equals 4 minus x. And the compiler compiles that to a function that computes f of x equals 4. That's an example of a misoptimization bug. What the compiler was trying to do is honestly simplify some of the intermediate variables in your function. It was trying to remove a lot of the boilerplate code, and it messed up. There are 6 new such bugs every month. Those bugs, on average, live 12 months. The numbers are eerily similar between GCC and LLVM. So 6 times 12 months, on every single release, every single commit number of GCC or LLVM, there are 72 misoptimization bugs that are documented reference on a confirmed issue on GitHub. Not to mention the one that might not be referenced, right? So do with that what you will. Those are just the facts that we have today. But notice that if you are betting $10 on a game of ZK Battleship, well, Alice is probably not going to give you precisely that program that they know is going to miscompile. But if you are playing a game of give me 1 million on my financial protocol, well, beware of what Alice might give you. Are you auditing the assembly, the RISC-V assembly? Because you really should. There's other options and more talking about this. I'm going to stop talking about this. But one last point I'm going to make is every time you have a compiler that compiles to a ZK proof, notice that a compiler bug is usually something we catch with unit tests, right? You get a compile function that computes f of x equals 4, right? You run it through 9. You're intending to get 4 minus x. You're supposed to get minus 5. You're going to get 4. You're going to think, oh shit, that 4 is not the correct result. Here's the problem with a ZK proof. You're hiding the inputs. You're trying to compute if the torpedo hits with respect to the position of your battleship, which you are absolutely not revealing at any point in the process. That's the entire point of playing ZK Battleship, right? You're hiding the inputs, and so the only thing you see is proofs that passed successfully. The ship were not hit, the torpedoes do not hit. And then your torpedoes have eventually covered the entire grid, and still you have not hit the ships. And the proofs are like, yeah, cool. There's no problem in your RISC-V ZK VM. I am not dissing RISC-V ZK VMs. This is not against VMs of any kind. This is just how compilers work today and the engineering data we have on what GCC and LLVM do. Okay, so there's a third model. The third model is called an abstract machine. We're going to go into what an abstract machine does, but here's why you should care. The productivity is as high as your high-level language if you favor the same language. The advantage and disadvantage is that this is language-specific. So I'm taking a high-level language. I'm taking your OCaml, your Haskell, your JavaScript, and I'm doing something that interprets that JavaScript directly. I am not compiling it to anything. I am using a machine that does not have any representation in hardware. So I'm skipping all of the steps that are there to model the hardware. My machine is resolutely abstract, it is minimalistic, and it has a single goal, which is to create a value out of the program and the arguments you gave. And it was designed in order to give semantics for a programming language on a whiteboard. Here's the use case for defining abstract machines in academia. Dear professor comes with a new programming language. They throw some syntax at the board, and then they wait. And they're like, dear audience, of course you understand how to compile with, how to compute with that syntax, right? Right? It's intuitive, right? And the audience, after a while, explained to that academician, no, it is not intuitive. You are indeed going to have to give us an idea of how that works. To which the academic was like, can I give you an implementation? I'm like, dude, you're an academic. We don't want to review your code. Like, this is very clear between us. Your code is not a thing we want to see ever. So here's a piece of chalk. Explain to us the semantics of that language. And so they defined abstract machines. This started in 1964. The first professor that did that was P.J. Landin. There's a crap ton of languages that have been defined in exactly that way over time. The abstract machines are by definition minimalistic because the guy that was designing them had a piece of chalk, and that's it. So, compilation to native code looks like you're taking your high-level code, you are compiling it to a sequence of instructions that compile, that represent the instructions of a machine. Even if that processor is a little bit abstract, RISC-V is there to paper over several processor semantics, but it is representing what the hardware would give you in terms of computation capability. It is representing details of that hardware. It is representing a very specific architecture. And then those real instructions, in some sense, are what you're proving over. If you are interpreting with an abstract machine, your control words are literally part of the language. And you are focusing on one part of the high-level program and saying, hey, that part of the high-level program, I can reduce it to something smaller. And when I say smaller, I mean literally syntactically smaller and simpler. And then I'm selecting another part of the program, and I am also reducing it to another piece that is smaller. Think of it like a compression function. Now, of course, if you're familiar with programming languages in the lambda calculus, what I'm doing is pushing symbols around, I'm reducing the stuff in question, I'm actually computing. But the core idea of abstract machines is the instructions do not correspond to any notion of processor or any notion of hardware. We don't, they, by definition, were not made for that. Here's an example, the CEK machine. It fits in 5 lines and in 1 slide. Now you're going to tell me, okay, sure, man, like this is an abstract machine that is a little bit too abstract for me, because on the first line you're going to see the source of the language, and you're going to see the source of that language represents a value, a lambda, or an application, and you're going to tell me, dude, I've been to class as well, thank you very much. This is the lambda calculus, this is not a real language, we're not interested in your ranting around a real language. Okay, you want to see the CEK machine applied to a real language? Cool. This still fits in a slide. I have 15 rules instead of 5, but it's still 15 rules, right? I have a real language, I have a real syntax, I have an if, I have a let construct. Now, of course, you're going to tell me it's Lisp. Whether it's it is a minimalistic language. Yes, that's why we chose it as a first milestone. But it is a real language, it has real production code in the real world, and it is still very, very, very small. Now, what you're going to notice in the bits that are in here is that I'm dealing with 2 mutually recursive functions, one that has 7, one that has 8 instructions, and I'm firing one of those instructions one after the other. They're just literally a decoration of the source code. I'm working on the source code directly with a minimal amount of bookkeeping. And so that abstract machine model lets me define how several functional programming languages work. In many of the cases that you see on that slide, here's the fun part. The abstract machine is authoritative. What does that mean? It means if you write, the C++ was defined by the implementation of its compiler. So people came up with implementations, and then they said, what's C++? That's C++. And then researchers spent years, literally, and I know some of them personally, writing the specification of C++ retroactively from the compilers. And they had a lot of problems when there were mismatches, inevitably, between the specification and the actual compiler. A lot of functional programming languages were defined differently. They started with the abstract machine. And then they went to the implementation, and if the implementation does not match what does not do the same thing as the abstract machine does, then the implementation is wrong and the abstract machine is right, by definition. Now, that does not mean you can't define an abstract machine for, say, Python, which is not in this slide. It's actually relatively easy to define an abstract machine for Python, but it means that you have to convince other people that this is the real true Python. Because the real true Python is defined by whatever was on Guido's laptop at the time. That is what defines Python. Python has a big dictator for life. If Guido says you're wrong, you're wrong. I don't care how much work you've done. So you need to convince people that you're doing the same thing as Guido's laptop. But it is very much possible to define an abstract machine for Python. Cool. Now, what are the consequences of that and why do you care? This kind of arithmetization is small and simple. Back in the days where we were only doing R1CS, now we are highly dependent on lookups, so the straight count doesn't really mean anything. But when we were doing only R1CS, we needed on the order of 12,000 constraints to make this. For your reference, this is half the size of the compression function of SHA-256. So you take SHA-256, you remove all the inits, all the padding, all that crap, you just focus on the compression function, you're down to 27,000 constraints, if my memory serves. I may be wrong, but this is within 10%, like it might be 24 or something, right? And I'm at half of that for defining an abstract machine that reduces a Lisp, a production Lisp at that. Right, and includes, you know, other very cool things such as hash counting and using Poseidon and an interesting amount of stuff. So basically, this is small. This discipline lets you do proofs using a small amount of work, which is why we realized we were working on the basis of Nova with slightly different choices 5 months ago, and we were 55 times behind the competition in terms of performance. Now, don't get me wrong, I don't want to put that on Nova. We were also, how shall I say, not as clever as we could have been. But over the last 5 months, we have not only ported that from an R1CS-based implementation all the way to an AIR-based implementation. We're now 3 times ahead of the competition. And this is not just small fields. Now, don't get me wrong, there are people working in small fields in the room. I will recognize small fields go really, really fast. I spent several years trying to convince myself that you could do it without small fields, and I was humbly recognized small fields really go really, really fast. But we've had the time to port that and also modularize things so that the next port doesn't require that much work. So the next time that we're going to need to implement that on Stew with a different form of algorithmization, that's not going to take 5 months. And when we need to implement that on Binius, that's certainly not going to take 5 months because we will have ported that on Stew maybe at less than 6 weeks, something like that. The other thing is, when you want to formally verify things, and verify that your stuff is correct, the nice thing about having a paper that tells you here's the reference model for the reduction of JavaScript is, well, that's my specification. So now I just have to prove that the implementation matches the specification. I don't have to invent the specification. And at those sizes, we will be done so fast it's going to make your head spin. The only reason that we are not done at the moment, and God knows we have people in the team that would like to do formal verification, is that we keep innovating on the back end and how to do those proofs. So it's very fun in terms of company dynamics. You should join. Argument is a great company. There's constant fights between people that are like, stop touching it, I'm trying to verify it. And people are like, no, 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 really, it could be better. So when I'm saying this can be faster, how much faster can this be? So we've done for you the cleanest possible and the most honest benchmarks. And this is so honest, I'm showing you a slide where I'm actually not faster. So here's the thing. The whole thing about abstract machines is that they go faster on the bookkeeping side of things. But if you have no bookkeeping, if your hardware representation has been made so as to do a special kind of computation really, 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 really fast, it turns out that saving on the bookkeeping doesn't save anything at all. So Fibonacci is the example of that. What that means is Fibonacci is putting stuff on your stack, adding them, putting more stuff on the stack, adding them, and so on and so forth. And that kind of permutation is already quite optimized. RISC-V will produce code that does that really fast with minimum amount of blah blah around the additions. And so it's really difficult to build SP1. So that you can interpret all of this, there's a blog post, you can read the blog post, have all of the detail, you can have all the code, you can reproduce all of this. I'm just giving you a very quick flavor. Sphinx is our slightly tuned variant of SP1. That is a fork that has minor differences. You have SP1 on the right. Lurk literally shares code with Sphinx. So we call into it as a library. We do not actually care about RISC-V at all. So of course we did not use a RISC-V prover, whether it's Sphinx or SP1, but there are some interesting functions and some interesting cryptography in there, including a fancy lookup argument. This is the cleanest differential benchmark you'll see ever. We're literally just implementing the thin abstract machine layer on top of a native prover and sharing everything in the prover, the good and the bad. We also have numbers for RISC-0 and Jolt. If you're interested, go see the blog post. So the pure Fibonacci of 50,000, of 10,000, not exactly faster, but when you're doing something, very esoteric, such as I'm going to take the vector of elements from 0 to 1,000, and I'm doing the Gauss summation, like I'm doing 0 plus 1 plus 2 plus 3 until 1,000. Turns out we're a little bit faster because there's a bit more bookkeeping involved. And when I say a bit faster, I mean a real bit faster. when you look at Fibonacci, there's one thing that has always frustrated us, which is that Fibonacci itself is computed in a messy way that doesn't actually even take advantage of the SIMD capabilities of the existing processors, if you think about it. So we thought, hey, or at least a genius among us, I'm actually not responsible for any of this personally, thought, hey, you know what? You can actually make Fibonacci go fast. And we have a fast Fibonacci implemented a matrix multiplication. 2x2 matrix multiplication, which will really actually make the stuff work. And there, well, there's a little bit of bookkeeping too, showing that RISC-V interpreted needs to figure out how to access the elements of that matrix. And in that bookkeeping, that now stuff works a little bit faster. So that's pretty cool. But there's more. There's more because a few years ago, like I told you, this whole abstract machine stuff started in the 60s, but in the 80s, people started figuring out, well, all of those abstract machines function the same way. They take your big, gigantic program and they focus on a part of it and they contract it. And then they figure out which next part of the program they need to focus on. And they take that part and they contract it. And then they go all the way over there and they figure out which next part to look at it and focus it. And so what you were doing with your bookkeeping was that you had a stack, and that stack was represented either in a native stack or a continuation stack, but really you were spending a lot of time contracting things, focusing on the interesting bit, contracting things there, and then reconstructing the larger program so that you could have access to the other control term that you were looking at. And so they were using the full trait schema at the bottom of this figure. And then people figured out, well, there's this discipline of refocusing that actually in dotted lines allows you to go straight to the, if you can predict which part of the term you're looking at afterwards, that they allow you to go straight to what which part you're going to contract. It turns out this is really difficult to figure out if you are reducing the term, but if you have reduced the term, you've run evaluation, not proving. You know everything that's going to happen, and so that refocusing thing, which is algorithmically very difficult to figure out, becomes trivial, and now you can basically do a proof plan exactly like the SQL query execution plans. And furthermore, this proof plan is actually a graph. I'm going to shut up because this is not my thing to explain. First, Chime has given a talk to it at the latest zkSummit that was much better than anything I would say tonight. And there will be a paper to appear soon that I'm not an author of. But to give you an idea of some of the goodies that fall out of that, this is a super duper mega optimized Lurk program. I don't know if this is what you would write, but I can guarantee you this is top level, like 10x programmer Lurk program. We have memoization for free. That is, if we can call the shots in advance to what we're going to reduce, we're certainly not going to reduce the same thing twice. And then you're going to tell me, but how does memoization really matter? Surely, you know, we know that there are programs that need to be memoized, with the classical example being dynamic programming. Because we have all gone to interviews at large companies, right? Maybe not the academics in the room, but the academics in the room were training us for the interviews at the large companies anyway. So we've gone to algorithmics, and you've had questions about dynamic programming, right? Dynamic programming is that thing that falls on every single interview, and you have just one way to go through it, it's memoization. And you're like, cool, so first it's a niche thing, and that dynamic programming thing is a thing that you will be requested to do on the interview. Typical thing, compute the longest common subsequence. Here we're benchmarking a longest common subsequence that is hand memoized in Rust. That is, that thing is actually doing dynamic programming techniques and actually builds a matrix with your intermediate results for the longest common subsequence. Those are the two bars on the right. We're actually optimizing the heck out of that, and then we're writing something relatively simple in Lurk by comparison, and we're getting something that automatically works quite a bit faster. Okay, so more in the upcoming paper. All of this is super cool, but this is the summary slide. This is exactly what we're doing with Lurk. The idea is, this is abstract machines. abstract machines are tiny, and because they're tiny, they allow us to explore a very large design space. We had a prover based on Nova called Arecibo. We have a prover that was based on SP1 that we call Sphinx. Our theme is that we are naming them after observatories. We like looking at the stars, and we're all romantics. But we will also explore languages. We've been on Lisp so far because we're fixing the backend. We're now embarking in an adventure to support Camel. And there will be more things in the future if we have the occasion to play with that very nice project. Abstract machines are a framework that let you do that, and that lets you do that for relatively free because, again, emulating hardware, very important if you're actually going to run on hardware, not so important if you're doing math. And that just diminishes the footprint of how much effort we have to put into every bit that we're doing. So that's Lurk. But in the process of doing this, and in particular in the process of doing this for customers, we've discovered a dark secret of our entire ecosystem. And this is valid whether or not you care about Lurk. I'm not selling you Lurk here. I'm selling you whether you care about not losing the nice things that you find on this slide. Proofs are awesome, right? Proofs are cheap to verify. The verification is negligible in computation time compared to either the actual computation or not to mention producing the proof. They're small. They're very nice. We even have all of those very fancy talks. There was one talk by Jens Groth, another one by the chief scientist at Aztec, which name escapes me at the moment, which recently rejoined the company, and all the jazz. Like they're really, really fantastic tools to reuse proofs and create a stream of proofs and link them together. That's fantastic. I have news for you, folks. You ready to cry? This is where we cry. This is where we all cry, right? As an ecosystem, who in this room does not work with blockchains at all? Oops, then we all cry, right? There's nobody that's safe, right? Because the moment you want to do anything on a blockchain, you cry. So here's the thing. The cost for verifying proofs today is what it is on Ethereum. And yes, I'm not the first one to notice this. You are going to tell me, yeah, sure, the price on Ethereum, price of gas on Ethereum. Everybody has agreed that the most, and we asked, the most they're ready to pay for the verification of a proof on Ethereum is 300,000 gas, which stands at a little bit over $5 these days, but they do not want to pay more. I literally have a customer in the room that I've tried to negotiate, like, could you pay a little, and they said no. Like, I'm not going to point him out, not to single him out, but like, the whole point is the ecosystem does not want to pay more than 300,000 gas for the verification of any proof. That's it. Which means that we're pretty much verifying gross 16 as far as Ethereum is concerned. I know that in L2s and coprocessors and other things, you can do other things, and that's great, and we should do those things. But what that means is proofs on Ethereum are gross 16 or maybe Plonk, if your Plonk verification is implemented correctly, at best. Other thing, the moment you had that fast verification latency, meaning on your laptop, you could verify things very quickly. The moment you're sending your proof to a blockchain, now you're in trouble because your proof needs to be not only included in a block, but it needs to do other things we're going to talk about. And then the streamable side of things is really about how you are able to create a stream of proofs that are linked to each other. I'll detail more on the universality. So what that means is, as I mentioned, 300,000 is an industry standard, which means that everybody is quick because they care at least about Ethereum, even if they're using also other places for verification, will finish their proof with a gross 16 or Plonk, at best, verification step. That thing adds at least 2 to 5 minutes to your prover time, just because you're forced to care about that protocol from 2016, which was a great protocol in 2016. Don't get me wrong, it is the most implemented in our entire industry. Do we want to be handcuffed to it forever, though? The other thing is, this is not really about block inclusion. There's some blockchains, like this would have been about block inclusion in 2018, but there's some blockchains that do block inclusion pretty fast. We're now relatively late. Like, you can get in the block pretty darn fast these days. Aptos will let you in 200 milliseconds. 200 milliseconds is fine. But because those proofs, the unit of proof verification costs upwards of $5 to $10, depending on gas price, everybody is forcing you into an aggregation model. They're saying, we're going to redistribute the cost of those $10 to the customer, and so we're going to wait until we have 5, 50, 500 customers, until we can divide that $10 by 5, 50, 500, and then we pass on those costs. And that aggregation and waiting for the other proofs is what is actually costing you in terms of latency. And then you have size limits. And those size limits are even harder to break in terms of blockchain. They're harder to break because blockchains actually enforce those size limits. They actually care about the size limits in ways that they wouldn't, where they would let you choose your own pricing model if you were to talk about execution speed. What that means is that proofs, insofar as you're verifying them on chain, are execution inputs. Execution inputs on a blockchain are sacred. They need to be kept around forever because the dogma is that your blockchain is not safe because it has many validators, or at least not only because it has many validators and your Nakamoto coefficient is very high. It is because you have full nodes. Your full nodes re-execute the chain and they hold the validators accountable to the protocol, meaning the number of honest full nodes you need to detect that the validators all, in majority, colluded and decided to go AWOL and do their own thing, is one. You need just one full node that will raise the alarm and say, hey, we have double spend on that chain now, which means you need to replace your validators and relaunch the chain with a new set of validators. Which means the full node must re-execute, which means the full node must have access to all the transactions, which means you need to store the proofs forever, and you do not have a choice on how much do I pay for storage. The price is one size fits all. There's interesting new storage models on Sui and Aptos. I'm well aware. Those are about the state consumption. They're not about the transaction consumption. Transaction is billed at a fixed rate for the entire blockchain. You cannot choose your own adventure. So the size of your transactions need to look like a transaction. This is what I call the MMS problem, which probably dates me. Because a transaction looks like an SMS. A proof, if you get out of the gross 16 Planck side of things, looks like an MMS. And remember how telcos priced us when we started having MMSs? The other thing is, most proof use cases are actually not a one-off. They're very often a stream of related proofs. If you're doing a ZK game, you're doing the moves of your ZK battleship example. If you're doing a bridge, you are submitting a proof about the latest block of a blockchain for which you already submitted a proof for the prior block, right? And you are using, whether you want it or not, because that's the only thing that makes sense to a blockchain, you're using the blockchain to link those proofs together. Even if you're doing a recursive proof, you're doing a recursive proof of all the game moves, the 50 game moves since the beginning of the game to now, but you still must, for the blockchain to accept that this makes sense in the game that you're running in a smart contract with Bob, you still must link even those 50 moves to the 49 moves, including in the prior recursive proof for the prior game. Which means you're using that blockchain to make the link, and if you're using that blockchain to make the link, you actually wouldn't need recursion. Recursion is irrelevant for you, because you would be pointing at the prior state that the validators have accepted. Which means that ZK coprocessors solve part of the problem. They are really improving the state of things. ZK coprocessors are great, but they don't solve everything because they are not a blockchain. They can't do that link between the new proof and a prior state for you. And then there are exceptions to this rule. I've been saying the state of blockchains is poor when it comes to proof interaction. It is. But there are exceptions. There are some blockchains that have figured out what being a proof-centric blockchain looks like. They are not the only examples, but Aleo and Mina are really good at it. They understand proof verification. They don't build you through the nose for it. They know exactly how to link it to a prior state. They have figured out that sometimes the size of those things is a bit problematic. okay, some of them do a bit of aggregation, fair, but really, blockchains do blocks, so they're really, really good. But what can you do with Aleo? You can speak to Aleo again, right? So if all of your proof activity lives on Aleo or Mina, you're cool. No problem. The rest of this talk doesn't concern you. It's a good time to tip your waitresses. But if you are interested in a little bit of a wider application of your proofs, then you might want to avoid this. So we're thinking that it's a good time to get feedback on actually how to solve all of those problems at once. And so the claim is, well, we regain all the nice advantages we got from proofs. We want proofs that are cheap, where even Stark proofs, on a horse trading basis, okay? Stark proofs can get very unreasonable very fast, but if Stark proofs are reasonable, then I will consider them small. My end of the deal is what I call the New York Times banner contract. The Stark proof needs to be smaller than the amount of data I download out of my browser on the top image of the New York Times, which in numbers translate to 100 kilobytes. If it's more than the New York Times banner, we're gonna have a word. Fast end-to-end verification latency, streamable, so that I can deploy my use case that depends on doing proofs over and over again on the same semantic state. I want a ZK bridge. We learned that doing ZK bridge, by the way. And I want no vendor lock-in. And so the idea is we can actually build a blockchain that offers you this UX. And we're very confident that this is a thing that is very easy and fast to build. You get sharded state. So sharded state avoids this conflict problem that when you are updating state, when two people are updating the same state and provide proofs updating the same state, very quickly you will realize that those two proofs are going to arrive to the blockchain and only one of them will go through. Because the other one updates the state from the same starting point as the other proof, which just updated the state, and therefore is now in conflict with that updated state. That is the Mina problem that a lot of blockchains are, I call it the Mina problem, but this is a problem faced by a lot of people that are usually bound to telling applications. It becomes now very complicated to develop an application on my programmable platform. The solution we like is a sharded state where it's very regulated, and that is the job of a blockchain to say who speaks at which time. There's one speaker per time. If you want to talk, you wait for your turn. And as you wait for your turn, and it is your turn, your proof is not in conflict with anybody else. Your transaction is a proof that advances your state, and you can send messages to other shards. Now you're telling me, Francois, you were saying there was no vendor lock-in. You're proposing to me another blockchain, that other blockchain is going to be a ghetto somewhere. How do I care about this? But wait, I have more interesting stuff. So first, I will tell you the answer to that question, but in between, I wanted to mention also that we don't have to have that aggregation model. That aggregation model and that verification on-chain on the L1 is here for security purposes. Why do you care about it? I don't have to wait that long to give you a full certificate of your transaction, your proof verification, its effect on the state that you updated. I can do that in a single one round trip. You will get a full certificate by all the validators, a majority of the validators of Proofcoin that will tell you, yes, your proof is valid. We have understood the state you wanted executed. Here is a cryptographic artifact that is signed by all of us, or a super majority of us to be technical, and that proves that this proof was valid, and you can take that certificate anywhere you want, because it relies on your ability to verify signatures. And every blockchain verifies signatures. Now this is usually the moment where the question, where I start getting the questions, is this a sidechain? It's not. It's not a sidechain, because I can't in 2024, I could in 2018, and I wish time was there as simple as that, tell you, yeah, sure, trust my validators, bro. I have 120 of them, and surely they can't all be colluding at the same time. But these days, where I can't tell you, trust my validators, bro, I have to do a little bit more work. So yeah, we know how to do that work, thankfully. The nice thing about being in 2024 is that other people have done that work. Yes, we need to aggregate. Yes, the validators need to collect those proofs. They need to aggregate them into one big proof. They need to send that proof to Ethereum. That proof needs to be verified by Ethereum. They also need to be bonded. They need to be bonded in ETH. And if anything is untoward with that proof, or you do not even have liveness, then this fully decentralized network gets its validators slashed. But that proof takes 30 minutes to arrive. And if it takes 30 minutes to arrive, I want the user to have a signal that validators that know that they will be caught in 30 minutes if they say anything untoward have deemed that their proof was indeed valid. So you get all the advantages. You get the advantages of the L2. Your validators are under the gun of being slashed if they do anything vaguely remotely non-kosher. But you get the feedback in a sub-second in one trip. Some more goodies. Because we have sharded state, we can do parallelized proof verification, which means if that thing becomes successful, we can scale the validators individually. They bring more nodes online. Your shard is a fully fledged blockchain with all the nice properties of a blockchain, which means Mina gives you 8 field elements to work with in terms of state. I don't know how much we're going to give you, but I think it's going to be a bit more. Lurk can be thought of, because Lurk produces proofs, that's its one job, as the main smart contract programming language of that blockchain. But you know what? We like the ecosystem. We suspect that you are not already all Lurk users, which is a thing we'd like to fix, don't get me wrong. But in the meantime, we would like to help you with your problems. And so you're probably generating proofs with something else. So we're going to verify that something else, all the something else's. We have an effort to standardize or universalize, have a reasonable implementation of stack verification, go to Adrian relatively quickly so that we can make sure that this universalized stack verification is useful for everyone. And then we can, because we have those shards, give you your own model for transaction storage. If you want to have transaction storage that lasts forever, we'll give it to you, and you're going to have to pay for it. But if you want your transaction storage to be stored for less time, and therefore pay less, with security consequences, we can give that to you while preserving the security of the entire blockchain. The shards communicate, they have messages, and yet we do not get shards that communicate messages that are deduced from something that has now disappeared. It gets a little bit fancy. I don't have the time for this today, but ask me once I've gotten a beer. And then once you've gotten that certificate in less than 1 second, you can take that certificate to any blockchain. That certificate only contains signatures. The one thing that every other blockchain knows how to do is to verify signatures. So you can take that certificate, get it verified for a price on any blockchain that will be epsilon compared to the price of a proof verification. And yes, you're trusting a set of validators, but you have the best security guarantees behind those validators that the ecosystem knows how to put forward. So we get back everything. We get back to a world where proofs are cheap, where even stocks are small, because again, it's choose your own adventure in terms of the length of the transaction storage. If you have problems with the security things, there are other remediations than paying through the nose for storage, and we can help you put them in place. The verifier's dilemma is a thing that as a community we've worked on for many years, and we know how to defend against this to something else than storing transactions forever. We get very fast end-to-end transaction latency. One round trip with a good connection these days is under 500 milliseconds. This is streamable. You get your own proof-driven chain, and you get to play with others as well. And there's no vendor lock-in, because you only need to care about us. We're domain-specific. We're not a generalist blockchain. You only need to care about our proof verification for the first second of your transaction. After 1 second, you've got our certificate. You can bring it to whichever settlement chain you care about. I've been told that there was this guy called Steve that did, oh, and there's one more thing. And so I've been told it was really interesting to do that thing for the one more thing. And you're going to tell me, well, okay, so this is very nice, but you're doing mostly Lurk. You have not been doing so much blockchain today. You have that nice project about blockchains. We'd like you to participate, actually. It would be really nice if we found a way to build that stuff communally. Don't get me wrong, we like VCs, but we like the ecosystem to move forward a little bit as well. But this connects back to Lurk. So you want the inner game of why we would do that eventually? Well, there's this one thing about distributed proving. We've been looking for distributed proving now for a while. Now, distributed is not proven networks, right? So there's another use case floating in the ecosystem, which is this proven network, which is really about matchmaking. Matchmaking is really considering I have 50 proofs from 50 users, and I have 50 provers, who gets what? It's a distribution and matchmaking problem. There's nothing wrong with that, it's just not the problem I'm talking about tonight. There's other people looking at distributed proving, which is I have one big proof, and I have 50 provers. Can I use the 50 provers to make the one big proof go faster? And that is a thing that cryptographers have worked on for a while. We have ways to break down proofs that are either ways to break down proofs at the proof boundary, or if you have mutually trusting provers, even within the proof. So you've heard about zero continuations. If we break that outside of the proof, you've heard about IVC, PCD, you've heard of folding, you've heard of recursion. There's many ways to approach this. All those approaches have been really focused about how to verify correctly that the proof was composed from the correct fragments and have a succinct way of doing that decomposition and figure out what are the constraints that are relevant. And this is great. This is great work, but it only concerns half of the problem. You need to actually figure out how to get the witness to the prover that is going to do a fragment of the proof. And if that witness is large, getting the witness to the prover is a lot of network bandwidth. Why is that witness large? The witness is potentially as large as the state that you've built up to the shard or the fragment that your new prover is going to start with. And the reason why is because you've built up a lot of witness and you don't know what that fragment of the proof is going to address within that witness. Now, because it is a fragment of the proof, it's only doing a part of the computation. Because it does a part of the computation, it's only going to address a little bit of what's going on. But you don't know which. So if you don't want your prover to just fail and crash in a miserable failure, you need to give him all the witness because, hey, he could tap into any part of the witness at any moment. And now you have a problem, which is, so we have those very fancy CPUs, and we even put GPUs on the provers. We forgot about putting fiber optic cables, and now the whole distributed prover network becomes very expensive. So the problem is a problem of encapsulation. How can you reduce the amount of state that you could possibly address in a fragment of the proof? There's no way to do this except if your proof did that in the first place, which amounts to distributed proving, or more exactly, proving distributed programs. Every single distributed program against pretty much every paradigm that you know about, from MapReduce to actors to freaking threads and logs sent over a TCP network, has, by definition, has had to assume, because it is about distributed programming, that you don't have a shared memory between all the people that are doing the work. That's the difference. It has said, yeah, there's no shared memory here. And because it has no shared memory, that thing is actually easier to represent in distributed proving because you have very clear bulkheads in between the bits that are not shared in the memory. And so this is what we can build with Lurk. Because we're operating directly in the high-level language, we don't lose the concurrency primitives through the compilation. So when you have, let's say, an actor's model that is expressed in your source language, you are now able to isolate different parts of your program that are communicating through message passing, and the only part that they're getting from the other parts of the system are those messages. And those messages are small. So instead of wasting your time on network bandwidth and then not actually making use of the CPU, you now have a small network bandwidth and you're making use of the CPU. So that's why we're interested in this, because the system we're thinking about that has those shards that pass messages between them, it is also a system that models that kind of actor framework, where you have a message passing primitive for concurrency between processes. So instead of updating a proof by updating one big item of state, you can update a proof through updating many shards that eventually converge to one final state. So your blockchain can actually become a proof coordination network as a side effect of all the good community-oriented features that we're interested in. Remember, cheap, fast verification, streamable, universal, all of those things lead to that very nice side effects, which is now we can orchestrate proofs. So Proofcoin matches actor-based concurrency. It can be used to do coordination of proving at a high level. All right. This concludes my talk. Thank you very much.